Hello and welcome. I recently learned how to use assembly language to access the floppy disk and to read bytes from a file. So in this video, I document that process that I used. So you're going to see the parts of the Unravelled book that I read, me using the MAME Debugger to verify how certain things are initialized, and then view what happens inside the buffers as bytes get read. And then toward the end, you'll see the assembly language code that I wrote and watch it in action. So if you're curious about the process I use, this video is for you. If you just want to see the assembly language code, feel free to skip to the chapter toward the end where I just show that assembly code. Let's go. My first stop this time was not the Unravelled series, but actually just the Disk Basic Manual, because there is a documented routine called DSKCON. So I read up on this, and it looks like everything you could ever want to do, you can do just with DSKCON. The catch is it's very low level. You really have to tell it exactly what track, what sector you want to read or write to. So let's say you wanted to read a file. Well, the directory is at a known sector, so you go read that sector, and it has a known format, so you interpret it according to that format. And then the directory tells you where the file lives, and so then you go to that sector and you read that. But then you gotta go through all this stuff, man. And there's already code to do that. It's already in the ROM. So I'm thinking, do I really want to do this? I mean, there is a nice advantage, not just that it's documented, but if there are any errors, you get to handle them. They're not going to go through the ROM error handling and then boot you back into the basic and show you the error message. So this is certainly a nice way to go if you want full control over everything. But if all I want to do is just read a text file and print it out to the screen, I think there are simpler ways. In the back of Disk Basic Unravelled, they give a list of the most reusable ROM routines that you might want to call. And sure enough, they've got one to open a disk file. They've got one to read a character from a particular disk file N. So this looks like it may be the way to go. And in fact, they even tell you how to call it. They tell you what to initialize. So first, accumulator A, you have to give it the mode. These are letters. A is a number. Not exactly sure what that means. You put the file number in register B. File number, what does that mean? Does that mean which entry in the directory the file is, the first file, the second file in the directory? Does this mean the device number? Is this something else? Okay, file name.ext in dynamp and default type, and I'm sure these are listed earlier so I can look at them. Oh, and we also have to initialize daskful and dffln. Okay, I'll look those up and I'll see what quote initialized means. So it'll open a file control block. Which one? Where do I get to the file control block? At first glance, it looks like I'm going to have to do some interpretation on my own. Maybe the most instructive use of this is to see where it gets used and to see how the caller initializes everything. So here is some calling code, and if we look at the comment, we see it's opening a sequential file. That's what I want. There are two kinds of ways to open a file. Sequential will just mean you're going to read or write one byte at a time in order, whereas a direct or random access file, you can kind of do whatever you want, wherever you want. I'm not interested in that. And now here I see what they mean by putting a letter in the register A. So they're actually just using the ASCII codes for the letters. I decided probably the easiest way to interpret this code is if I just step through it. So I decided to write a simple basic program to do what I want to do in assembly language, and then use the MAME Debugger to do assembly level debugging on the code that runs as a result of my basic code running. And that basic program should also be triggering this second routine, this console in. So before I get that going, let's take a look at what this code is going to look like. So at C5, C4, that's how you read a single byte from a file. So it starts here, so it hopefully saves some registers for me. This is handy for me, so this is now pointing to the file buffer vector table. And that table lives right here at 0928. So the idea is we've got 2 bytes times 16. So there are 16 different buffer vectors, 1 for the system and 15 for the user. And this is likely all those device numbers, like numbers 1 through 15 that you can choose when you're opening and writing and reading from a file. So this tells you, if you know which one you want to look at, this will give you the address. You go into here by that number, indexed by the number, and it'll tell you the address where that file control block lives. And you can see here now it's just doing a little bit of math. It's taking that number, multiplying it by 2, and then using that as an index into this block here to find the FCB you want. This -2 is because the B is 1 based, but obviously this indexing is 0 based. So this kind of shifts everything to the left a bit, so that when B is 1, it'll shift it back to the right, kind of compensates for that. So this is the simple basic program. We're going to open a file for input. I'm going to use device number 1, and I'm going to just open test.asm. And then we have a loop. At the top of the loop, we check to see if we've reached the end of file, and if so, we're done, we close it. Otherwise, we read the next full line out of the file into $. We wait until a keystroke, and once there is, we go and print that line, and then we loop back up. The test file that I'm going to use, that I'm going to read in, just has a bunch of things, bunch of letters here. In fact, you know what I'm going to do? I'm going to make it super clear that we're done with the file by adding DONE at the end. So what I'm doing is deliberately having a file that's bigger than a sector, but not like exactly 2 sectors. So I want to see what happens as I read this file, because it's going to fill up a sector buffer, and I want to at least see what happens as that buffer gets filled up and then refilled up, just to make sure that as I'm reading stuff that I'm going to be doing it the right way. As usual, I'm using Toolshed to copy files into the virtual disk that I'll be loading up into XROR or MAME. And I'm copying 2 kinds of files. One is this text file that I'm using as my sample data, and one, of course, is the basic file. So for the text file, I'm going to be using this type, text editor source file. And I am going to do this perform end-of-line translation. I always do -R because I keep doing different versions and I want it to update whatever last version I had. And I will be doing A for ASCII. So this is the command that I'm using to copy it over. So this is the command I'm using to copy it over. And then for the basic file, pretty much the same command, but instead of -3, I'm using the default, which is -0 basic. And I'm using the T, the tokenizer. And I should be ready to start debugging. So my first breakpoint is going to be where the file gets opened. And this will allow me to see exactly how BASIC fills in those parameters that Unravelled was a little bit unclear about. And so I can see just what BASIC does, and then I can emulate that in my own code. And here we are at C48D. First up, A should have the mode, and so A is set to 49. I think I can use this to verify that the ASCII code is what I think it is. Let me see. Probably have to put that in double quotes. Maybe I should just use the register name. Oh, I'm being stupid. Printf. There we go. There's my I. Okay, so we're opening as input. So the file number should be in the B register, and I see the file number that they're opening is 3. Wait a minute. I'm not actually looking at my call to open the file. I'm looking at the systems call to actually load the disk read basic file. And this is where we reset. And I don't set the breakpoint this time. And I separately load my basic program. And now I set my breakpoint. And now I run the program. Okay, so A is 49 again. Now the file number is 1. That is more what I would expect. Now let's take a look at the file name and extension. So they were called denamv, and the thing that comes after denamv. They start at hex 94C. And sure enough, we see our test Asm. And check this out. There's all this space between them. T-E-S-T. These 20s really are spaces. So what's going on is it will space pad the right side to make it exactly 8 characters. And then we get our Asm. There's no dot. It just knows the first 8 characters, the name, and the next 3 are the extension. And next there are just 3 areas that get initialized, and it doesn't say how. The first is this. This is the disk file type. So let's see which one it picks. This is what I put when I saved it. Let's see if it actually is a 3. So D file type is at 957. And it's 1. So probably what's happening is because I'm using maybe an open command, then it's treating it as a data file. Maybe there's another command where it would treat it separately as a text editor source file, but I don't think I care. I think I can just do whatever BASIC is doing. So using 1 maybe would be fine. Maybe using 3 would be fine. Next up is daskful. That's the ASCII flag. So it's either going to be a crunched BASIC or a binary file, which is 0, or it's going to be an ASCII file, which is FF. I'm guessing this should be FF. That's at 958. Which is the very next character, and yes, at least that's what I expect. That's an FF. And finally we have DFFLen. This is the direct access file record length. Now I'm not doing direct access, so I think this doesn't matter. So I think whatever is here is probably just going to be uninitialized garbage. But let's see anyway, 97C. So I see hex 1 and then hex 00. This is certainly not going to be the exact length of that file. I seriously doubt it's exactly this. So my guess is that whatever this is doesn't really matter. So I think this covers all of the parameters. So next I'm going to set a breakpoint each time we read in a character from the file, and that'll help me figure out exactly how it figured out where the file control block is, and I can actually look at the file control block and see what happens. At C5, C4. And here we are at C5, C4. So I'm going to be paying attention here. We're going to load X with those file buffer vectors. We're going to load B with devnum. So this will at least help me confirm that this should be 1. I think the device number should be 1. So we save our registers, we clear out that flag, we load X to point to the buffer, file buffer vector table. We load B with devnum, and B is 1. Okay, good. That makes sense to me. It should be 1. And then we multiply that by 2. Now it is 2. And then we use that to index into X. And so now X is pointing at A8A, and we can take a look at A8A. And lo and behold, I see all of those bytes from my file sitting here in the buffer, as well as some other stuff leading up to them. So these control bytes, and then there's the sector buffer that comes after it. So the first thing we do is we load B with the very first item in the FCB, which is this instruction, so it's the FCB type. And so the type is hex 10. So we see B is hex 10. So Unravelled helpfully tells us about these control bytes. It says what the offset is, what the name they chose for it is, and then a description. So that very first thing, the FCB type, hex 10 indicates sequential input. And if I continue reading through this code, I'm going to probably jump over here until I get to the sequential file. And here's where we deal with the cache. So that sector cache is going to have all the bytes that we need until we use it up. And so this tells us how the cache gets cleared, whether we need to read an extra buffer load of bytes from the disk or not. And that looks like what this is doing. And one of the things I'm going to need to know, since I'm doing this myself, is when I have finished reading the file, is there like an EOF? And yes, there is this thing called the DFL. This tells us if any data is left. But that shouldn't be confused with this, which is the number of characters left in the file buffer. And I really want to make sure I'm interpreting these things correctly, so I'm going to keep my eye on these in the debugger. So these are indexed into the file control block. This is telling me how many characters are left in the data buffer, and this is telling me whether anything is left in the file itself. So it's going to hit FF when the file has been depleted, and it's going to stay 0, 0 as long as there's still data. But then another question would be, well, have you depleted the file just by reading the last sector worth of bytes into the buffer, even though you haven't used the buffer yet? Like, there's just so many ways to interpret this. You've got to use a debugger to see exactly when this thing flips to FF. So the interesting offsets are 23 and 24. So this is going to be offset 16, 17, 18, 19, 20, 21, 22, 23, and 24. So it's going to be these 2 bytes right here. So what I'm going to do is just continue until I hit the breakpoint for the next time I read another character, and we're going to take a look and see how these things change. So you see immediately that one became FF. So that should mean that there are 255 characters remaining in the buffer, and this 00 tells us there's still more in the disk file to read. Continue, and this keeps counting down. So I'm going to hold this down and watch what happens when that gets down to 0. Okay, so lots of things changed. When that went down to 0, we replenished our buffer, and now we've got that done at the end. That's why all these bytes afterward changed. So this became a D6 because it's not a full buffer worth of bytes, just a D6 worth of bytes. We're still at 0, which is good to know. Oops, we ran out of string space. I forgot to clear some string space. So let's clear, let's be safe, 500 worth. And while we're at it, let's protect everything above 3EFF. And so we keep our eyes here again. I don't know what's happening now. We seem to be hung. This is off executing goodness knows what. Control is not. Oh, of course, I have to hit a key. Forgot my own code. I have to hit a key, and then it prints that string. And now we're back here at the breakpoint again. And so we can watch these change some more. One left to go. Alright, so you'll notice as soon as we read that last thing from the buffer, that's when we switch to FF. That's when we switch to say that there is no data left in file. So that's very nice. I don't have to worry about how big the buffer is and how much of the buffer I've read. I can just rely on this to tell me when I've read the last thing that belongs to the file. And I should be able to hit a key and everything got printed, including done. So now I'm ready to start writing some assembly code. So here's the code I came up with. I'm not 100% sure about everything here, but it seems to work. I am definitely not the authority on how to write this kind of code. I'm just learning this myself. So up at the top we have some equates for some RAM memory addresses for many of the settings that we need to set. So I went over this earlier in the video. This is the one offset into the file control block that we actually need to deal with. This is the location of where we can find out if there's still anything left to be read out of the file or if the file has been depleted. And then these are the locations of the ROM routines that we're calling. You'll notice, by the way, I am calling the character out routine or putcher. In past videos, I just would directly poke bytes and then make my little fix-ups for the characters that I cared about. But now I might be reading an arbitrary type of character, like not just lowercase letters or not just the colon, but like anything. So I'm just kind of relenting and then using the ROM routine to do that translation of the bytes into ASCII for me. The downside of this is that it's not as easy to put things where I want on the screen. This is really good for just like printing one character at a time, left to right, down the screen. And that's really all I need, so this is a fine thing to use. First thing we do is we open the file. Let's see how that works. This is where we set up all of the flags and settings and everything we need so the file gets to be open. That's why I use the debugger to figure out how BASIC sets everything up. We start off with the file name. This looks like more code than it really is. All I'm doing is I'm copying 8 bytes from my little file name location into where the ROM wants it to be. So for example, I have file name set up to be test2. You'll see that I am padding it out with spaces so that it's fully 8 characters. And here's my extension, txt. And so all this is doing is copying from file name to dynamf. And then this is just copying from filext to dextbf. Next thing is the ASCII flag. So I'm setting that to be FF to mean yes ASCII. That sets this. They want the B register to hold the device number, so I'm setting B to be 1. I'm also putting that in devnum. I might not need to do this. I'm not sure if the ROM always does this. The Unravelled book didn't say I had to, but I'm doing it anyway. And for whatever reason, it looked like the file type was set to 1, data file, when I ran it under the debugger, even though on disk it's actually 3, which is text editor source. But I'm just doing whatever the ROM did, because that seemed to work. And finally, I'm setting my A register to be I. That means I'll be opening it as a sequential input file. And then I get to finally jump to the actual routine. I could do a JSR and then return, but instead I'm just doing a single jump instruction, and then the RTS from within here will act as my RTS and will bring us back to main. Talking about going back to main, let's go back to main. Now that the file's been open, I can go into the file control block, and then I can find that end of file flag, which I need to use as I'm reading from the file so I know when to stop. So first, what this does is it goes into the array of vectors. So this is a table of locations of FCBs. So I go into that table and I pluck the very first one because I'm using file number 1. So now U is going to point to that file control block. And then this offsets U by the flag, the end of file flag, or as they call it, the FCB DFL. I think it's data file left. Tells us if anything is left in the file. Okay, so now I have my loop. I go into that flag and I get the value and I put it in A. And I ask if A is FF. If A is FF, we have reached the end of the file and we go to done and we return back to basic. Otherwise, I set my device number to 1 because I'm going to read a character from that file, and that's what this does. And then I set my dev num to 0 because I'm now about to print to screen. And that's what this does. And fortunately, this only needs its input in the A register, and this puts its output in the A register, so I can just call one right after the other. And then I just loop up. Here's the test file that I'm using. I just put a nice sampling of characters, uppercase, lowercase, numbers, punctuation, and then like some sentences and stuff. And let's run it. And there it goes. So you can see, you still see my loadm exec up here. And that chur out routine just works just like print. So it just started printing right after that command. And it looks to match what's in the file. And then it was done and returned right back to basic. So I hope you got something out of this video. Maybe the main takeaway is to experiment whenever you find ambiguity in documentation. There's nothing like just running it using a debugger to see how a known working example does what it does. In this case, that was my basic program. And then you can duplicate that in the code that you write when you write it from scratch. As always, thanks for watching.